this is angular momentum for drum only. This is angular momentum for the sand particles which are still sticking to the inner wall of this drum. This is angular momentum of the outer drum. स्टूडेंट्स, आज के इस वीडियो में हम रोटेशनल मोशन के ऊपर दो कठिन तो नहीं पर ट्रिकी क्वेश्चंस करेंगे। आइए देखते हैं हमारा आज का पहला क्वेश्चन। क्वेश्चन कहता है अ हॉलो ड्रम ऑफ मास m1 एंड रेडियस a rotates freely with an initial angular speed omega naught. This is a hollow drum. It is a hollow cylinder. It is spinning about its own central axis at an angular speed that is omega naught. Just a minute. It is spinning about its central axis with an angular speed omega naught. A second hollow drum of mass m2 and radius b is initially at rest, although it is also free to rotate about the common axis of the drums. Then there is second drum. This is a hollow cylinder. It is also free to rotate about the same common axis. Both the cylinders, both the drums can rotate about one common central axis. This is initially at rest. There is no initial angular speed of this drum. Only the inner drum is spinning with some angular speed omega naught. Radius of the inner drum is A and that of the outer drum is B. Mass of the inner drum is m1 and mass of the outer drum is m2. And both are free to rotate means there is actually no friction in the axle. जो axle है वहाँ पे कोई friction नहीं है. A thin layer of sand of mass small m is distributed uniformly on the inner surface of the inner drum. This is inner drum. Inside the drum, there is a thin layer of mass that is basically sand, which is uniformly spread. This is drum, and inside this drum, this inner surface, there is a thin layer of sand which is sticking to the surface of the drum. Okay, mass of the sand is small m. At t is equal to 0, at time t is equal to 0, the small holes in the inner drum get opened and the sand starts flying out at a constant rate of lambda kg per second. This drum has got some narrow pores, small holes, tiny holes, and at time t is equal to 0, these holes gets opened. That means this is our cylinder, this is our drum which is spinning. There is a thin layer of sand inside it. There are many pores, there are many holes on the surface of the cylinder, and at time t is equal to 0, somehow all those pores gets opened up. So the sand starts coming out from these small holes, and the sand starts flying out at a constant rate of lambda kilogram per second. Every second lambda kilogram of sand is thrown out. The sand particles stick to the outer drum, and these sand particles fly and stick to the outer drum, the inner wall of the outer drum. Ignore the transit time of the sand. That means imagine that a sand particle which is thrown out from the inner drum immediately reaches the outer drum. There is no time lag. And write the angular speed of the two drums as a function of time. The question says that write the angular speed of the two drums as a function of time. आप सभी को चाहिए कि वीडियो को पॉज कर दें और खुद से एक बार जरूर सोचें कि क्वेश्चन का सॉल्यूशन कैसे करना है। आइए इस क्वेश्चन को मैं आपके लिए सॉल्व करता हूँ। ये इनिशियल सिचुएशन है। ये इनर ड्रम इनिशियल एंगुलर स्पीड ओमेगा नॉट से स्पिन कर रहा है। यहाँ ये सैंड की लेयर दिखाई गई है थोड़ा सा ग्रे कलर में, और थोड़े समय के बाद लेट अस से आफ्टर टाइम टी, दिस इज टाइम टी इज इक्वल टू 0 and let us say this is the situation at time t. In time t, lambda into t mass of the sand has got deposited here on the inner wall of the outer drum, and the remaining sand is still there on the inner surface of this inner drum, right? So some sand is there on the outer surface, inner surface of the outer drum, and there is some sand which is still there on the inner surface of the inner drum. So at time t, lambda into t mass of sand is here, and remaining mass of sand which is there is m minus lambda into t. Just a moment. I am sorry. So remaining mass of the sand which is there here present on the inner drum is basically m minus lambda t, right. So the question asks you to find the angular speed of the two drums as a function of time. Say at time t, this drum is rotating with angular speed omega a and the outer drum is rotating with angular speed omega b. So we have to write omega a and omega b as a function of time. The most tricky part of the question is that you have to realize that the angular speed of inner drum will not change when the sand particles are thrown out. Yes, angular speed of the inner drum will not change when the sand particles are thrown out, because if a sand particle is thrown out, it comes out along with its momentum and angular momentum that it was having when it was sticking to the drum. It is something like this, like in terms of, if I talk in terms of linear mechanics, suppose there is a cart of mass m and there is a boy or a monkey, whatever monkey, riding on this cart, and the whole thing is going with velocity u. Now if suddenly the monkey jumps vertically up relative to the cart, will the velocity of the cart change? The answer is no. If the monkey suddenly goes up with some velocity relative to the cart, monkey has gone up like this, but it has jumped vertically up, okay, that's fine, but it is having this motion in its body, that motion has not changed. So if this momentum of monkey has not changed, why will the momentum of this cart change? So the velocity will remain unchanged. A similar thing happens here. This particular sand particle is already having some angular speed or some speed, and when it comes out, when it just comes out, its speed has not changed. So its angular speed has not changed. So actually its angular momentum about this axis has not changed. I mean, sand particle is just sticking to the drum and now it is just out of the drum. In these two scenarios, the angular momentum of that particular particle has not changed. You have to understand that. So if the sand particle that is thrown out, its angular momentum has not changed, why will the angular momentum of the drum change as such? There is no way. Should not change. So it will not change actually. So angular speed of the inner drum will remain equal to omega naught all the time. It is just not going to change. When the entire sand comes out, then also the angular speed of the inner drum will remain omega naught only. So we have answered the first part. The inner drum has a constant angular speed. What about the outer drum? Outer drum has gained some mass, and in fact those sand particles, they have landed on the drum, and when landing there, they were having some angular momentum. So there could be some changes here, right? There could be some changes here. Again, you can compare it to this situation, like if a cart is moving with some velocity u, and suppose there is a tree out here, a monkey is hanging from this tree, and the monkey suddenly leaves the branch of the tree and falls on the cart. If the monkey lands vertically like this, after the monkey lands on the cart, will the velocity of cart change? The answer is yes, this time it will change, because just before hitting the cart, monkey was having a downward velocity, but there was no horizontal momentum in the body of the monkey. There was no horizontal movement of the monkey. But after the monkey lands on the cart and it has stabilized itself, that means slipping between the feet of the monkey and the cart surface has stopped. The monkey is now stable on the cart. After it has stabilized itself, this whole thing is going with some velocity v. So now m plus m mass is moving with velocity v in horizontal direction, whereas just before the monkey lands, only m mass is moving with velocity u in horizontal direction. So horizontal momentum just before monkey lands is this much, but after the monkey lands, the horizontal momentum is m plus mv. So these two quantities should be equal, as there is no horizontal force acting on the system as such from outside. So the velocity has got changed. Similar thing will happen here, but we will have to talk in terms of angular momentum rather than linear momentum. So let us do that. How can you do that? Very simple. Let us consider the situation at time t. Let us consider the situation at time t. Think about this, the whole thing as a system. Okay, that will make writing the equation even easier. Consider this whole thing as my system. Now, what is the angular momentum of this system about this axis at time t? About this axis, pen is the axis. We are trying to write the angular momentum of the system at time t. So, for this inner drum, the moment of inertia, inner drum, is m1 into a square. Am I right? It is a hollow drum, and so if it is a hollow drum about this axis, the angular moment of inertia is simply ma square, mr square. So ma square into omega naught, because the angular speed of this particular drum is still omega naught at time t. I am writing the angular momentum at time t. So I omega for the inner drum. Now there is some sand on the inner drum, right? How much sand is there on the inner drum? How much sand is there on the inner drum right now? M minus lambda t. So because this sand is spread uniformly on the surface of the drum, the sand is also a kind of drum only. So its moment of inertia will be m into a square. The layer of sand is also forming a drum of radius a only here. So the overall moment of inertia of the drum along with the sand will be m1 a square plus m minus lambda t a square. So okay, I have written it separately. For drum this is the angular momentum, for sand this is the angular momentum, the sand which is still sticking to the inner drum. So at time t, this is the angular momentum of this drum and sand is sticking to it. What about the outer drum? What about the outer drum? Let us say the outer drum has got angular speed omega b. So mb square is its moment of inertia into omega b, that is its angular momentum, and this much amount of sand has piled up here. So for sand we will write lambda t m b square. Again, this sand is also nothing but a thin cylinder, so its moment of inertia is m into b square. So lambda t into b square into omega b. Am I right? So this is angular momentum for drum only. This is angular momentum for the sand particles which are still sticking to the inner wall of this drum. This is angular momentum of the outer drum, and this is angular momentum of the sand particles which are sticking to the outer drum. So this is the whole angular momentum of this system about this axis at time t. You may please note that there are, we may imagine that there are actually no sand particles at any instant of time between these two cylinders, because the question says that neglect the transit time of the sand. That means sand moves out from here and immediately lands on this wall. That is what the question is asking us to assume. So there are negligible sand particles present here. We can just ignore it. Either sand particle is here or it is here, right? So this is the angular momentum at time t for the entire system. And what is the initial angular momentum? What is the initial angular momentum for the inner drum and sand? I am taking it to be together. Just a minute. This is the complete moment of inertia of sand plus drum omega naught, and the question says that the outer drum is stationary initially, it is not rotating. So for this isolated system which is experiencing no torque from outside, its angular momentum about this axis should remain conserved. So this angular momentum at time t should be equal to this angular momentum, isn't it? Just by simplifying this you will get the value of omega b. and it is quite easy. Actually this term cancels out, right, and ma square omega naught, this also cancels out. Can you see that? So it is quite easy to simplify this. You can simplify it for time and you will get the value of time. You will get the, I am so sorry, you can simplify it for omega b and you will get omega b as a function of time. Do it on your own. This is equal to this. So this cancels out, this cancels out. So basically the remaining terms are equal to 0. You just separate the terms containing omega b, bring them on one side of the equal sign, and you will be able to calculate omega b. So I hope this is clear to everyone. Now after some time, the whole of sand will get thrown out of this cylinder and it will land onto the outer cylinder. Okay. At that particular time, you can again calculate the final angular speed of that cylinder using this same expression, because the whole sand will be ejected at a time t when lambda t is equal to m. Please, lambda kg per second is being thrown out. In capital T seconds, this much mass of the sand is thrown out. If this is equal to given mass of the sand, then the whole sand is out. So just by substituting m by lambda in place of t here, you will get a value of omega b that will be the final angular speed of that particular cylinder. So this is expression of omega b as a function of time from 0 to capital T. Capital T is the time when all sand is out, it has landed on the outer cylinder, and after that angular speed does not change. I hope all of you have understood this. Now let us move on to next question. Read this question please. A mass m is attached to a post of radius r. This is a post pipe kind of thing. A mass m is attached to a post of radius r by a string. There is a string which is holding this mass. Initially it is a distance small r from the center of the post and is moving tangentially with speed v naught. Now students, please take a note. This radius is capital R. This is a cylindrical pipe kind of thing and radius of that pipe is capital R. And this mass is initially at a distance of small r from this central axis, right? And at a particular instant, this mass is having a tangential speed of v naught. This is what the question says. And this is a different diagram. This is a different diagram. In this case, and in this case, there is a difference. The difference has been explained here. The string passes through a hole in the center of the post at the top. Here the string is passing through a hole. Actually, it is a kind of pipe with a narrow bore. This is a pipe and there is a small hole here through its length. So there is a particle which is going around it like this, and the string is passing through the pipe. The string is coming out of the pipe from the bottom, right? This is the situation here. The string is gradually shortened by drawing it through the hole. Now this string is passing here. If somebody goes and just pulls the string gradually, the word is gradual, gradually you pull this string will get smaller in length. So this mass is initially rotating with some initial angular speed v naught, and you start pulling this string down. You can imagine, for simplicity, just imagine that this mass is going in a circle on a horizontal table, a smooth table. Forget about the effect of gravity. Like this is the situation that there is a tabletop. This mass is going in a circle of radius r initially with speed v naught. There is a small hole here. The string comes here, and you can draw the string down through this hole. So this is the first situation. Now the second situation is the string wraps around the outside of the post. In this second situation, the string has been wrapped around a solid cylinder like this. So when the particle moves in a circular path, the string just wraps around this post. It just winds around the post. Now the question says, what quantities are conserved in each cases? Quantities means momentum, angular momentum and energy. Basically question is asking you about whether momentum of the particle remains conserved, whether the angular momentum of the particle about, let us say, this point remains conserved, or whether the kinetic energy of the particle remains conserved. What kind of quantities remain conserved in these two cases, find the final speed of the mass when it hits the post for each case. If you keep on drawing this string, the mass is ultimately going to hit this pipe. Similarly here, if the mass goes on and on around the post, after some time it is going to hit the post. So in which of these two cases, rather in both the cases, we have to find at what speed the mass is going to hit the post. This is the question. I hope you have understood this. Now students, this is well, I will use this diagram only. I think it is visible. Okay, I will draw a bigger one. In the first case, the mass is going in a horizontal circle like this, and you can just pull this string through this pipe. Now what will be happening? The velocity of the particle initially is like this, but if you draw this string like this, this tension force will be performing some work on that particle. Can you see that? Because as the mass spirals around this post, that means as the radius decreases, obviously we can say that this mass is getting closer to point O. So this distance r is decreasing. So the tension force is acting towards point O, and there is definitely a movement of this particle towards point O. So when there is some velocity in the direction of force, the force is definitely doing some work. In fact, this force is doing some positive work on this particle. And you all know from work energy theorem that if a force performs positive work on a particle, its kinetic energy is bound to increase. So what will happen, as the string gets shortened, जैसे जैसे रस्सी छोटी होती है, the speed of the particle will go on increasing. So speed of the particle v is definitely increasing. Is kinetic energy conserved? Not at all. Why? Because the string tension is doing some work on the particle. Is momentum conserved? No. Why? Because there is certainly an external force, the string tension, acting on the particle, and if there is an unbalanced external force, there is no question of momentum remaining conserved. Momentum तो conserved है ही नहीं. In fact, direction change हो रहा है तो ऐसे भी पता है कि momentum conserved नहीं है. But if I talk about the magnitude of momentum, that also does not remain conserved because v is definitely increasing. Now what about the angular momentum of the particle about O? Is it conserved? Certainly, because this tension force is passing through this point O, so this tension does not have any torque about point O. So the particle does not experience any kind of torque about point O, therefore angular momentum of the particle about point O also remains conserved. Angular momentum of the particle about point O is conserved. Students, because angular momentum of the particle about point O is conserved, using this fact, we can easily calculate what will be the speed of the particle when it hits the post. The radius of its circular path goes on decreasing, and when the particle hits the post, actually at that very instant it is moving in a circle of radius small r. ये ऊपर से नीचे नहीं आया है, प्लीज मेरे ड्राइंग को समझिएगा. कैसे समझिएगा, मैंने गलत बनाया है तो गलत है, ये अच्छा नहीं लग रहा है, इसको थोड़ा सा बदल देता हूं. इसका रेडियस ये चल रहा है, इसी टेबल के ऊपर घूम रहा है, इसका रेडियस ऐसे घटता यहाँ पे आके खट से लग गया इसको. तो फाइनली just before hitting the post, just before hitting the pipe, the particle was moving on a circle of radius capital R maybe, right? So just using angular momentum conservation you can find that. The final angular momentum about point O will be mvr, isn't it? And this should be equal to mv0 r. So from here you can calculate the value of final speed v just before it manages to hit the post. You can also find what is work done by the string tension on the particle. How can you do that? You can find increase in kinetic energy of the particle, half mv square final minus half mv square initial, that is change in kinetic energy of the particle, and it will be equal to work done by string force on the particle. In the second case, I will just draw this. I am just drawing the cross section, okay, of the pipe. This is the cross section of the pipe. Now look at this situation. The particle is somewhere here initially, let us say. It is moving at speed v naught. After some time, the string wraps around this cylinder and the particle will be somewhere here, right? The string is just getting wound around that cylindrical pipe. So, can we say that angular momentum of the particle is conserved about this point? Can I say this? Can I claim this? The answer is strict no. Why? Because about this particular point, there is a torque acting on the particle. The tension force in the string, has a torque about 0.2. So, because there is a net torque acting on the particle about the concerned point, we cannot claim that its angular momentum will remain conserved about 2. In fact, it will change. Are you getting my point? But what about its kinetic energy? If you look at the situation carefully, particle is tied to a string and it is moving. The string is always under tension. Mind you, in this case, the string can remain under tension even when the particle moves this way. Reason being, this length of the string is being shortened by pulling it down. If there is a pulley like this and a string is passing over it like this, the string can remain taut if this length of the string increases and this decreases. It is very much possible. It is very simple. Because I am drawing the string down, even if the particle gets closer to 0.2, the string is remaining taut, isn't it? But in this case, if there is a component of velocity of the particle about this contact point, about this point, the string will get slack, it will get loosened. If there is any component of velocity, I mean, if the particle is moving with a velocity in a direction somewhat like this, then velocity component is this way, which means this distance is decreasing, which means the string will get loose. So, we all know that a string is not going to get loose. So, it simply means that at any instant of time, the velocity of the particle will stay perpendicular to the string. And if the velocity is perpendicular to the string always, then tension force has no power, it is not doing any work. So, power of the tension force is 0, work done by tension force is 0, wherever the particle goes, this just goes on decreasing and decreasing. After some time, this is the situation, isn't it? So, particle is going on a path like this, okay. After some time, it is going to be like this, and soon after this it is going to hit the pole. But at any instant of time, the speed of the particle, the velocity of the particle is perpendicular to length of the string. Therefore, tension is not performing any work, and if there is no work done on the particle, its kinetic energy will remain conserved. Very important. So, speed of the particle will not change. Though angular momentum of the particle about 0.0 will keep on changing, but speed of the particle is not going to change, and because the speed is not going to change, so magnitude of momentum will not change, but okay, momentum as a vector is definitely changing, no doubt about it, but speed is not going to change. So, the particle is going to hit this post while traveling at speed v naught, which is same as the initial velocity, right? It is always traveling. I just omitted it, you know why? Because I made a mistake there. a particle is always traveling perpendicular to the string. So, it is somewhat going to hit it like this, isn't it? Somewhat normally. Okay. But at the instant it is going to hit the surface of the cylinder, its speed will remain same as the initial speed. So, this is the solution to this question. The questions were not at all very difficult, but I think you have learnt a concept or two, and thank you for watching this video. Help me in increasing the subscribers. It is only you who can do that. If you have liked it, please do subscribe, and see you in the next video. Thank you.